Hi, this is Dr. Simon Romero. I'm here to present you the video tutorial for section 14.4, the chain rule. These are the topics that we will cover, and these are the practice problems. As always, I suggest you to do them. So the idea is the chain rule is just a way to taking derivatives of composition of functions. Composition of functions is just taking one function and then after that taking another function. So in this case, the chain rule is going to tell you how in functions of one variable is what's the derivative of f with respect to x. Now, the idea for our case is every time that you have a plane curve, in other words, a parametric curve, you can take a t and then just plug it into the parametric curve or a vector function, and you end up with x equal to something that depends on t and y equal to something that depends on t. And what about if you plug in that into the function f of two variables? So that ends up being something like this. So in other words, t depends indirectly on f. And the question is, well, how much? Geometrically, what is happening is you just have a curve here, and you're restricting your inputs only to the plane curve that we have right here. So in other words, we're just restricting the inputs of f to these points right here. And that gives you a particular curve in the graph, and the thing that we're saying is c depends indirectly on t, and the question is how much. So x depends on t, y depends on t, so the question is how much, since c depends on x and y, how much c ends up depending on t and how much that is. In order for doing that, we're going to remember what is the chain rule, and the chain rule says that if you want to take the derivative of a composition of functions, you'll take the derivative of the outside, evaluate on the inside, times the derivative of the inside. This first expression is not going to be very helpful for us, but it's exactly the same. We can write it in this way. How much h depends on t is how much h depends on u and how much u depends on t. So notice here, f depends on u depends on t. How much h depends on t, how much h depends on t is how much h depends on u and how much u depends on t. Well, so the question is, what is the rate of change in our case of c with respect to t? So here comes the idea of the chain rule. The idea of the chain rule is the following. How much c depends on t, it's given by two things. How much the change due to the change in x and the change due to the change in y. In other words, how much c depends on x times how much x depends on t tells you how much c depends due to the change in x, plus how much c depends on y times how much y depends on t gives you the change due to the change in y. So in total, c depends on x and x depends on t, and how much c depends on y and y depends on t. When you add all those two changes, you obtain the total change of c with respect to t. This is the proof. I'm not very interested in you completely remembering it. I just want you to get a flavor of why this is true theoretically, and it comes from the definition of differentiability. So we have, if the function is differentiable, this happens, then I divide by delta t, then letting delta t goes to 0, the thing that we have is that the limit of delta t going to 0, delta c over delta t is just the derivative of c with respect to t, but on the other side we have the sum of the limits. But the sum of the limits end up being like this, and notice that this goes to 0, this goes to 0, so we end up with the chain rule that we want. And that happens just because of the definition of differentiability. I don't want to spend too much time on this, so I'm just going to move on to an example. So let me compute how much the derivative of c with respect to t. So from the first equation, c depends on x and y, so I can compute how much c depends on x and how much c depends on y, and those are the expressions. From the other two equations, we know that x depends on t and y depends on t, so I can compute how much x depends on t and how much y depends on t, and those are the particular expressions. So using the chain rule, case 1, how much c depends on t is how much c depends on x, how much x depends on t, plus how much c depends on y, and how much y depends on t. And then I just plug in the expressions, and that's the result. Notice that in this particular case, plugging x and y is fairly easy, so I just did it. Sometimes plugging x and y is going to give you that you will need to do a long algebraic expression in order to simplify it. So in a celebration of learning, if you just get to this answer over here, it will be more than enough. So let me give you the idea for case 2. The idea for case 2 is pretty similar to the idea for case 1, actually uses the idea from case 1. So suppose now that you have that x not only depends on one variable but on two variables. X depends on s and t, y depends on s and t, and now we have that c depends on x and y. So indirectly c depends on s and t. How much c depends on s and how much c depends on t, that's going to be our question. So we can ask how much c depends. In this particular case, let me just work only on how much c depends on s. So in other words, we're holding t constant. So if we hold t constant, the only variable that we have here, once we hold t constant, is just s. So how much c depends on s is how much c depends on x, how much c depends on y, and compute how much x depends on s and how much y depends on s. Notice that this is just case 1, so pretty much case 2 is just doing case 1 twice. So let me just tell you what is case 2. So c depends on x and y. Suppose that you have a function that is differentiable on x and y. And suppose that x depends on s and t, and y depends on s and t, and both of them have partial derivatives. So c depends on s and t indirectly. How much? This much. C depends on s. How much c depends on s is c depends on x and x depends on s, plus how much c depends on y times how much y depends on s. And the same thing for t. So again, c depends on two variables, x and y. And both x and y depend, let's say, on s. So how much c depends on s is just given by these particular two branches of using the case 1. And the same thing for t. So notice that taking these two branches give you the partial derivative with respect to s, and taking these two branches give you the partial derivative with respect to y. I'm sorry, with respect to t. So let me compute those partial derivatives if we have these expressions. So again, c depends on x and y. How much? So we can compute how much c depends on x and how much c depends on y. From the equation, from this equation, we get that x depends on s and t. How much? Well, this is how much x depends on s and how much x depends on t. The same thing for the other equation, y depends on s and t. How much y depends on s is given by this, and how much y depends on t is given by that. Now, how we put them together? Well, using the chain rule case 2, how much c depends on s is how much z depends on x, how much x depends on s, plus how much c depends on y and how much y depends on s. And the same for t. So we just need to plug in the corresponding expressions. Now, the thing that we have here is, notice that plugging x and y is going to give us kind of like convoluted algebraic expressions that actually I don't think that I'm interested on simplifying. So I am not going to plug in x and y. However, actually in a celebration of learning you don't need to do that neither. So let me move on to the general version. The general version is pretty much the same thing. You have that one variable depends on n variables, and each one of those n variables depend on n variables. So the thing that we have is how much u depends on all those variables is given by those partial derivatives, and how much each one of these variables depend on the particular t's is given by that. So again, let's say you want to compute how much u depends on t2. So how do you do that? It's pretty much the same thing. How much u depends on x1 and how much x1 depends on t2. That's the first one. How much u depends on x2 and how much x2 depends on t2. And so on until you get to the last one. How much u depends on xn and how much xn depends on t2. And that gives you that over here. And that finishes the chain rule, the most general case. So now we're going to talk about a consequence of the chain rule, that is implicit differentiation. So first I'm going to remind you what is the implicit differentiation of functions on one variable, and then we're going to try to do an easier way to get the implicit differentiation. So let's start with this one. So we're trying, the implicit differentiation is how to take how much y depends on x when you have an equation, not necessarily a function. So the idea was the following: you graph your equation and you assume that y depends on x. Then you take the derivative both sides with respect to x, and then you obtain that. Notice that this expression is given by the chain rule. So automatically the chain rule is going to tell you dy dx. We don't have dy dx, actually dy dx is the thing that we want to find, so the chain rule automatically throws you the thing that you need. So you just solve for it and you obtain your answer. So now that we're going to try to formalize what we were doing in the old implicit differentiation. So we have a formula, an equation that has x and y equal to a constant. So in other words, we have a function of two variables equal to a constant. So assume that y depends on x. So in other words, we're assuming that y depends on x here. Then we take the derivative both sides with respect to x. This is a chain rule. Notice that in here we're taking how much f depends on two variables, x and y. And these two variables depend on x. Well, x obviously depends on x, and y depends on x because we're assuming that. So we take the derivatives, so f depends on x depends on x, how much f depends on y, and how much y depends on x. And the other side is equal to 0 because you are differentiating a constant. So notice that since y is a function of x, the chain rule is used. So how much x depends on x is equal to 1, and then we send this partial derivative to the other side. That's why we have this minus over here. And then we divide by the other partial derivative, and that's why this partial derivative is in the bottom. So notice that that gives you a rule that it works always, no matter what equation you have. And that's what we want to rescue from here. So given an equation, the derivative dy dx is just given by the partial derivative with respect to x over the partial derivative of y with a minus. The reason why they are switched is because of the process that we did before. F of the partial derivative with respect to y was multiplying dy dx, and that's why it's in the bottom. So let me just try to do an example. So I'm going to do exactly the same thing that we did before. So notice that in here the function of two variables is x squared plus y squared. This is one side of the equation. The other side has to be equal to a constant. That is the case. So now we compute the partial derivatives, and then we use the implicit differentiation formula. Notice that we get exactly the same. Now, why we want to use this implicit differentiation formula is because we can do more complicated things, like for example this one. We do exactly the same thing. We need a function of two variables such that the function is equal to a constant. So I'm going to send these to the other side, and then we obtain a function equal to a constant. Then we do the same thing. We compute the partial derivatives with respect to x and with respect to y, and you use the implicit differentiation formula. Notice that this is way faster than doing the old implicit differentiation. Now we can do implicit differentiation with three variables too. So the thing that we do is exactly the same thing. We have an equation equal to a constant of three variables, and then we assume that c depends on x and y. Then we take the derivative of both sides with respect to x. Then notice that since c is a function of x and y, the chain rule is used. And the thing that you have to notice here is x depends on x on a rate of 1, y depends on x 0 because it's an independent variable. So the thing that we end up having is exactly the same formula as before. So the thing that we have is how much c depends on x is given by this formula, and how much c depends on y is given by that formula. Using the same, more or less the same logic as we had before, we can remember this formula. So let me give you an example. So if you want to compute these partial derivatives, you need to compute, first of all, figure out what is your function by just sending everything that has variables to one side, and that will be your function. Then taking the partial derivatives with respect to x, y, and z, and then just matching them in the corresponding way. So notice that it's not that difficult to do this kind of process. And with this, we finish our video tutorial. Thank you very much.